And you guys have been seeing me using the smartboard in this fashion. Cope with my handwriting, please, and let me know I can slow down at any moment. Okay, question number one. Question number one. What I do, guys, for remember, this will be PDF'd and it will be recorded too. Just FYI, PDF and recorded, but on the network for you. Okay, question number one about the energy cost. Energy cost. And here's what the question, my friends. I have a bunch of lights. Here's my light. And these are L light. These lights, I have 10 of them. 10 lights. Each one of them is 100 watt. 10 lights, each one of them is 100 watt. And the cost, it cost us a kilowatt hour is 10 cents. It costs 10 cents for every kilowatt hour. The question for you is, if I run these for 10 hours, I'm going to run these. So this is the cost. Run for 10 hours per year. If you run that baby for 10 hours per year, how much will it cost you per year? What's the cost per year?
10 hours per day per year?
10 hours per day for 10 hours per day for a year. That sounds better, huh?
Yeah.
10 hours per day for a year.
Is your year 365 times 25?
365 is good enough for us. We'll leave that fraction. Okay, so simple. I have a bunch of lights, 10 of them, and one branch circuit, and just find me the cost. Any question guys about this? 10 lights, 100 watt each. The price that we're paying is 10 cents. How much would it cost me to run these 10 lights for 1 year? If they're running 10 hours a day. Okay, I use the answers when I do the answer in a different color. Any question about the concept? Okay, so I'm going to say here, cost per year equal, and here's the formula that we use, guys. We use the watt times the cents, or the price, I want to say just in dollars, times the hours, times the days, right? What else are we costing? So we have watts times dollars. I divide the watts by 1,000, and it's actually, this is usually in cents, and I divide the cents by 100. Everybody knows why? Let me minimize my email, close my email if you guys don't mind. Close window. Yeah. Okay, so that will close my email so it doesn't bother you. Okay, so I have the watts multiplied by how many cents, how many dollars, multiplied by how many hours, multiplied by how many days. Did I miss anything? Why did I divide by 1,000 the watts? Because we pay per kilowatt. Why did I multiply by hours? Because it's also paid per hours. And why did I divide by 100 the cents? These are cents. Oops. Why did I divide the cents per 100? Because to make them dollars. And the days. Okay, plug and play. So I have 1,000. Oh, the number of we have to also multiply them by the number of how many lights. N is how many fixtures, multiplied by how many fixtures. Okay, so 100 divided by 1,000, multiplied by 10. Everybody knows why 10? Multiplied by another 10 over 100, multiplied by how many days? What's with the 10 today? Everything is 10. Multiplied by how many days in the year? 365. Done deal. Any question guys about that? So basically convert the watts into kilowatts, the cents into dollars, multiply them all by each other. What do you get? I need two gentlemen or a gentleman and lady to agree on an answer.
I got 36.
$36? Anybody else got something similar? Are you sure it's $36? Did you multiply by 365? 100 watt divided by 1000 kilowatt multiplied by 10 of them, multiply by 10, divided by 100, multiply by 10 again for the hours and the days. What do you guys came up? Seems low. Phil? How much?
$36.5.
0.5?
$36.5.
36.
50 cents.
$36.5. Everybody came up with this? $36.5. Are you guys okay? 1,000. So that will be 0.1 times 10 times 0.1 times 10 times 365. 3.65, right? Everybody came up $3.65 a year. $36.5 or almost $37 a year. Any question, guys? So it really, the formula, this one is just to convert to dollars, and this one is just to convert to kW, right? Everybody knows that why that divide by 100. Any question, guys? Write the formula, bring it with you. I don't mind. Did we do anything wrong with the calculation, Phil? I thought here's the number. I put the number right here. Just flip 10.
But I mean, you got the N times the box practice sets, hours and days.
Here's the 10 for the cents. Here's the 10 for the numbers, and here's the 10 for the hours. Are we missing any other 10? I just flipped them. If it makes it easier, so put 10, just to make it like the formula says, you can do a 10 times 100 divided by 1,000. Makes sense? Just to start with like the formula is stated. Any question, guys, about this? Any question?
I do it on Excel, I get $365.
You guys gave me this number. Let's do it. Is that?
It's $365.
So where did you? 365. So we're off by 10. 365. Thank you. 365. When we do the calculation, I really would like two people, guys, to agree on one thing. 365. So we didn't multiply by 10. Any question about this? So this question number 1. Formulas with you. I don't care if you bring in the cheat sheet, there's the formulas, but there isn't a whole lot of formula here. Can I move to the next one? Okay. Question number 2. Question number 2, my friends. I have a piece of equipment. You're going to hear Chad a lot talk about piece of equipment. This piece of equipment it's sucking out of the system 50 amps, and the voltage of this system is 480 volt. Taking 50 amp at 40, power factor equal 100% unity, 100% power factor. 100% power factor. Okay, system. And the system is single phase. A single phase. Right? Can you have a 480 single phase? Yeah, you get 2 phases. So that's the system that you have, 50 amp 480 single phase, power factor 100 on the load, sucking. By the way, this little bulb here is always a circuit breaker, right? Because you have to tie everything to a circuit breaker. Okay, what's the question then, Chad? The question is, find, let's put the find TP, true power, and AP, and apparent power. Piece of cake. So I need to find AP. What is the AP? What's the apparent power for the system? Apparent power for the system. It's a single phase, so the formula is I times V. Do I have to multiply by 1.73? No. Okay, so you have your I. What's your I? 50 amp. What's your V? 480 volt. What do you get? 50 amps times 480, you get 24. 24 kV and A. 24 kVA. Piece of cake. Find the apparent power. Apparent power is always the amp times the voltage. No power factor. The second one that we need to find is the true power. True power is always the amp times the voltage times power factor, as you guys know. So it's the same thing, 50 times 480 times 101, because, and so check, that'll give me 24 kW. That's it. So both of them are the same because the power factor is unity or 1. Now Rob, had the power factor being different, what do? You just add by that percentage, multiply by that percentage. Zach, my friend, cool? Any question, guys? So if on Monday, if I give you a power factor of 80%, would you be able to do that? Cool. True power and apparent power are a big concept. Questions about that? True power and apparent power. Move on to next. Yes, no? Slow down. Next. Okay, question number 3. Question number 3, my friend, is size transformer for load. So you have a load, and I want you to size a transformer that feed this load. You guys have an issue with that? Transformer that can feed this load. And but you need something about the load though. My load is, this load is running at 208 volt, and the amps that's going in this load is 200 amps, and that baby is single phase. I have a load or a panel. I have a panel or a load that's a single phase, 208, sucking 200 amp out of the system, and I need to size a transformer that power or feed this load. Size a transformer. I want to remind you of the single phase aspect of it. How do you size a transformer for the load if you know the amp and the voltage? In another word, I'm asking you for what? Apparent power. I'm asking you for the apparent power. Do you see anything about power factor? When we size transformers, power factor, open the window, throw out the window. We don't care too much when we size transformer about power factor. So let's go to directly. So basically, I'm asking you to find the apparent power. Find the apparent power here. The apparent power equals Mr. Current times Mrs. Voltage times nothing else. No power factor. Any question, guys? So it's single phase. So if you go here, you take, what's my current? 200 amp. What's my voltage? 208. Always divide by 1,000. I don't do it. From now on, guys, with me, I always size in kW, assuming always divide by 1,000. When we talk power, we talk K. We don't talk volt amp in the power. We talk kVA when you size transformers and so forth. So if you do all this, baby, you end up with 42 approximation kVA. 42 kVA. So the size of each transformer is going to be 42 kVA. Next quarter, I want to get you to, not this one, next quarter, I will be asking you guys when we size transformers to go to this DeWalt and find me a transformer size, actual transformer size. You know what? Actually, why don't we do that? Since you guys have DeWalt with you, everybody has DeWalt with you. I usually worry too much about transformers when we go second quarter, but if you have DeWalt transformers, so I didn't have it on mine. Grab DeWalt, would you? So that would, I think it was 6 that talks about transformers. Motors are 6. Transformers. 7. Chapter 7. So I'll get you exactly where we need to be. 7, 7. Okay. So you take the 42 kVA DeWalt. You're going to take it to DeWalt 7-6. If you guys go to page 7-6 in DeWalt 7-6, what's the next standard? 42. Single phase, look at the voltage, 208. What's the next? Really don't look at the first column. You don't even need to worry about the voltage. The first column. You go from 25 to 37.5 and all the way to what? 50. Everybody can see 50? Single phase. 7-6. So this will be a 50 kVA transformer. 50 kVA transformer. Everybody got that? The first column, if you go to 7-6, right? See that table there, 7-6? The first column, it starts at 1, 3, 5, 7.5. These are standard sizes, but my size is 42, so I need 42 or more, right? Not less. So my options are 37.5 or 50. So where am I going to go? 50. So, and this is the arrow where you can go. That you go up. Yes, sir.
Yeah. Is it same for you to have the lesser KVA and move to the higher one?
Yes. If this is your load and you need a transformer to feed that load, you need a transformer that can give you the same kVA. But if it's not a standard kVA, what do you need to do? Go up. Yeah. This is like you have 3 children and you can buy a car that can fit 2.5. Either you get rid of one of your children or your next standard either 2.5 or 4. You're going to go to 4, right? That makes sense. It's kind of cruel.
Says in the book it has to be 10% greater than the load. I wouldn't know if in the book. So you know,
10% greater than required by the load. The transformer must have a kVA capacity 10% greater than the load required by the load. That's for the, later on we'll say continuous load. Leave this until the end. I didn't say anything about continuous load. If it's continuous load, usually I add 1.25 actually, pump it up a little. You have a good point. Any question guys about this? So all the sizes fill of the single phase transformer are right here. So next, I'm not going to force too much of that one, guys, but we're going to be using DeWalt a lot as we go through. Questions? Move to the next one. May I? Okay, where are we here? Number 5? Are we at number 4? I thought we finished them. Okay, number 3, number 4. Okay. So, okay, 42. Number 3, number 4. Number 4. Question number 4. Question number 4. I have the same thing. I have a load. All I'm giving you about the load, guys, my load is 100 kW. And I will tie a transformer to feed that load. But the power factor for my load is 90%. I have a load of 100 kW, and the transformer, the load is 100 kW. and the power factor is 90. Size transformer. Size XFR is always for transformer. Find me a transformer that can feed a load of 100 kW at 90% power factor. Now, some of you, did they put, is this single phase or three phase? Did they say anything about the phase? Does it even matter if I give you the kW and a power factor, if it's single phase, three phase, or doesn't matter? If you get the kW, guys, doesn't matter. If I give you the amp and the voltage, I need to know the phase. If you get the kVA or the kW, it really it's an energy. It's power. Power doesn't matter. I can deliver kW, 100 kW with single phase transformer or three phase transformer. Okay. Anybody has any idea how to size a transformer based on this? I want to remind you the rule is the formula that we use. Apparent power equal true power over power factor. Where's my, we always size based on the kVA, the apparent power. True power, so what's my apparent power? 100 kW divided by 0.9. Huh? Yeah, the true power divided by the power factor. Did they write it? Yeah, it's going to up it. It's going to up it. If you do that, you're going to end up with 111 kVA. 111 kVA. If I did my math right. Any question, guys, about this? That's how we size the transformer. Now then, I'm going to use red. Then you take your 11 kVA, 111 kVA, D Walt 7-6, exactly the same page that we were on, D Walt 7-6. And Zach, my friend, what's the next standard transformer? I go 7500. What's my next after 100? 125. So where do I going to go? 125. So my next standard is 125 kVA transformer that's going to feed this load or this building. Any question, guys? So Tao, my friend, grab that formula with you. Now, I want to remind you, when I went to this, I assume it's going to be single phase. This is where I made the decision, right here. I made a decision it's going to be a single phase transformer. I made a decision that it's going to be a single phase transformer. Right there at this moment. Now, just for the heck of it, I want you guys to do a three phase. I changed my mind. I want to take this and do a DW. I want to feed it from a three phase. So you go to 7-7 this time. Go to 7-7. I decided to make a three phase transformer. A three phase transformer, not a single phase. I want a three phase transformer to feed this load. Can you guys do, so 100, what's my next? Zach, do you have a 150. 150. So my next is 150 kVA. So if I decided to go for a single phase, 125, three phase, 150. Why standard? These are not in the code, guys, the industry standard. I guess you can get any transformer with any kVA, but you're cheaper to follow up the standards. Where do you get them? 7-6, 7-7. Any question, guys? Any question? Go to 5. Go 5. Question number 5. Question number 5. Question number 5. I have a piece of equipment. Always you're going to see Chad draw always piece of equipment. My piece of equipment. First, let's put the system. The system is 208 volt single phase. I have a 208 volt single phase. The equipment here, the power factor for this equipment is 150 kW, and the power factor of this equipment, my friend, is 90% power factor. Efficiency of this equipment is 80%. This equipment is 80% efficient. And the system is single phase. We talked about single phase system. Okay? Are you guys with me? Piece of equipment, 15 kW from China, power factor 90, efficiency 80. I am tying it to a 208 single phase system. I need to find the current for this equipment. How much current this equipment is going to suck out of this system at this voltage, at this frequency, at this voltage, at this power factor, and at this frequency. Big deal, because if I find the current, William, my friend, I multiply by 1.25 size over computation of the conductors. I want you guys, if you have DeWalt, to go to 1.4, all the formulas that you need in 1.4, in DeWalt 1-4. 1-4. So it's a single phase, and I'm looking for amp when horsepower is given. No, this is for the horsepower. We have kW. It's really this is very similar to, if you guys look at 1-4, everybody -1-4. And I need the first row says amp when horsepower is given, single phase. See what it says, direct current single phase. You're looking at single phase, except I'm not giving you a horsepower, I'm giving you a kW. So instead of horsepower times 746, you just put kW. Okay, here's the formula. Let's use this. So I need I equal kW divided by the kW, the power. Here's the formula that you need. kW divided by the current, divided by the voltage, because we need the current, divided by the power factor, divided by Miss efficiency. That's the formula that you need. The kW, this one here, guys, this is coming from a simple formula that says efficiency equal true power out, oops, I don't know how to spell out, true power out over true power in. Anyway, this is the origin of this formula. So the current that this equipment is going to take equal the kW, the rating of this equipment, divide by how efficient and its power factor and by its voltage. Piece of cake, you take 150K, divide by a voltage system with 208 single phase, multiply it by the power factor is 0.9, and multiply it by 0.8. And if you do your math, my friends, right? Did I put it right? 15K. You're gonna 50. Did I say 15?
You said 50.
You said 15.
No, I'm sorry. Can you guys change this? This should be, really doesn't make difference in the process, but this should be 150. This should be 150 kW. Sorry for that. Can you guys flip that one to 150 kW? 150 kW. Just to match what I have. The answer should be 579 amps. So, anybody came up with something different?
About 519.
150 divided by 0.8. You know what? Did they say single phase? You're right. It's a single phase. Yep. What's your answer? I'm doing it for 3 phase, but what's your answer? 590. Yep. 590. Yeah. 519 amp. 519 amp. 519 amp. Any questions about this? 150 divided by 2.8 times 0.8 times 0.8 times 0.9. 150. Sorry, 150. Now, can I have attention, guys, for a second? Tomorrow, if I give you the load as a three-phase, the only thing you're going to add, if that was a three-phase, what do you do here? 1.73. 1.73. 1.73. Can I have you to write this one here? If that was a three-phase, the only thing you need to do, Phil, my friend, is multiply the voltage by 1.73. Yes, sir.
I don't know how you guys get that.
Me neither.
Okay, let's do the math. 150.
Yeah, Chris is
150 divided by 208
Quantity.
times 0.9 times 0.8, close it, equal, times 1, 2, 3. I came up with 1,001 and 2, 1,002. Nick, my friend, you lost your 8. Oops, did I see that? What did you say? 1,002 amps. Okay, everybody came up with that. Sorry, you must have pushed a different button, Nick. Everybody got with 1,002? 1,002? Yeah, did you forget
Well,
that?
see, I've got a simple calculator, but I like it. And
That's
it gives me
okay.
Parentheses.
Yeah, parenthesis is a major
So,
difference.
that's why.
Yeah. Guys, when you use calculator, I can put a class on calculator, scientific calculator. When you do this in a scientific calculator, you put this number, divide, open parenthesis, multiply all these, close parenthesis, and equal, depending on your calculator. Yeah, you have to use a calculator, right? Do you use Casio or Texas Instrument? Yeah, Casio work different than, as you know, Texas. Texas is different.
You can calculate on the screen too.
Use my calculator. Yep. Any question, guys? 1,002 amps. If I ask you tomorrow, please, Chris, or on Monday, if I ask you for a three-phase system, the only difference is what do you do here? 1.73. 1.73. Okay. Shall I go to the next? No? Yes? It's really the voltage, but it end up the whole thing. Yeah. Guys, if you multiply, take this, I times V, if you multiply 1.73 times I times V, it's you basically multiply the whole quantity with it. So for all practical reasons, it's really everything here will be multiplied by 1.73. But what it means, it's really you modified only the voltage because three-phase, but it affects everything. May I go to 6?
So you're multiplying the suffragette, right? Not the quantity and the suffragette.
The meaning, it's you modify the voltage. If you want to do it in an Excel sheet, I will modify the voltage. Then if you modify the voltage and you multiply by anything else, everything is multiplied by that number. But what it means, you modify the voltage because now instead of having two voltages, two hots, you have three hots. You need to contribute to the three hots coming in. Can I move? No? Phil, my friend? If it's a three-phase, I did it actually here for a three-phase. If you're three-phase, I get that one. You end up with 579 amps, 579. If you want to do it for a three-phase, guys, your answer should be 579 amps. Did it? Yeah. That's why I wrote 579 in the first one.
Well, it's ironic that he sort of agreed with the 5 minutes.
Yeah. Okay, move. Yes, no. All right, so number 6. Question number 6, my friends. Question number 6 says, I have three-phase system. Here's my three-phase system. And get used to chat, guys. Draw all this stuff for you from now on. I have a load connected, and another load connected, and a third load connected, right? I have three-phase system. Each one of these, this baby is carrying 10 amps. This baby is carrying 15 amps. And this baby is carrying 30 amps. And these are phase A, phase B, phase C, and miss neutral. And miss neutral, right? Three-phase transformer feeding a three-phase, a three-load single phase each. So 10 amps, 15 amps, and 30 amps. They're not balanced. They're not balanced. My question for you, what current the neutral here, I neutral is going to carry? How much current I neutral is going to carry? How many amps? Are you with me? A transformer. Normally this is a big fat box here, right? And these are different loads sitting lights. These could be lights, by the way. These are lights. And right in between them, of course, there's a panel, a bunch of other things. So, unbalanced three-phase system, three phases giving you the amps, find the neutral. Here's the formula that you're going to use. I neutral equal, you guys remember that big formula? I A squared plus I B squared plus I C squared minus, make sure you put your brackets, I A times I B plus I A times I C plus I, which one we didn't multiply, I B times I C. Close the brackets. This is all right here. Should put my brackets right in here. Everybody's there? The formula?
Is that a square root symbol?
Yeah, this is all. This one is. This one all square root. Sorry. Equal square root. All these under the square root. Write this formula, bring it with you. Let's do the math. I have to see where we have them here somewhere in D-wall. Same formula. I'll find it for you. Okay? When you guys are giving you enough time to write it. Okay. No, it's somewhere here. We'll figure it out. Okay, let's go plug it in. You guys mind if we start plugging? I'm going to use red, so it's equal square root of. All right, so the first one is 10 raised to the power 2 plus 15 raised to the power 2 plus 30 raised to the power 2 minus, in my case here, 15, 10, times 15 plus 10 times 15 here plus 8 times plus 10 times 30 plus 15 times 30. 15 times 30. And all what you have to do is do the math. And the hardest thing is getting the math right if you're not good with that. Should be 18 amps. Anybody came up with something different? Should be 18 amps. 18 amps? Phil, did you guys? Not even close? 43? Okay. Here's a mistake that a lot of people do. You have to add all these, then subtract them. Add everything here, then you subtract the total. There's a brackets here. Using brackets because it's a big deal, right? As we all know from the days of arithmetics. Let me know when you guys are done and you came up with the same answer. Came up? Yeah. Make sure, the key point, guys, is to square these and add them up all. Then multiply all this side, add this, and subtract it from the squares, the sum of the squares. Okay. Almost there. Let me get you. I know you guys need a quick break here, but I'm almost done. So 6, 7, 8. So let's do number 7. Number 7 is very easy. Question number 7. Question number 7. I have a single phase system with the following current. Single phase. And there's a load here. So I have 30 amps coming in and 20 amps coming on this leg. And this is single phase system. Single phase system. My question for you, my friend, would be is find the current I neutral. Find I neutral. That's piece of cake, right? Find I neutral. Single phase, remember, single phase. I neutral equal 30 minus 20 equal 10 milliamps. Done. Very easy, straightforward, no gimmicks, nothing. The last two are very easy, straightforward. Any questions guys about this? Can I move to the next one? Yeah.
In the formula for the single phase, do we always subtract the bigger
From the smaller, yeah.
Not doesn't matter the line.
Doesn't matter the line. The largest number from a smaller number. You're absolutely right. If this was 40 and this was 30, 40 minus 30. The largest leg from the smallest leg amp. Okay. That's piece of cake. So that was number 7, right? So number 8. By the way, we have 10 questions. I should have told you that. 10. We're almost there. So I know you're thinking. Question number 8. Question number 8 is really interesting. I have two. Okay, I have. Let me draw that one. Okay. 20 amp. Here's what I have. I have a 90 watt fixtures that's running at 95% power factor. The voltage system is 120 volt. This is light. This is light. It's non-continuous. Non-continuous. So you don't have to worry about it being continuous. Non-continuous. Don't have to worry about it being continuous. And I have, as a matter of fact, 200 fixtures. I have 200 fixtures. Each one of them is 90 watt and the power factor for each is 95. The question is, how many circuits of 20 amps do I need for these 200 fixtures? They're non-continuous. Don't ask me where would they be. They're not continuous. They're not going to be there for more than 3 hours. Highly unlikely in a commercial building though. They're not continuous, so don't worry about the continuous. Am I clear about that? 200 of them. The question is, I have 200 of these lights. How many 20 amp circuits do I need? How many 20 amp circuits? How many 20 amp branch circuits needed? Right? How many 20 amp circuits needed to feed all these 200 lights? Non-continuous. You encounter this all the time, guys. Okay? The first thing we need to do is find the apparent power. Apparent power, because we always equal true power over power factor. So what's the apparent power for the light? Because we don't size based on watts, we size based on volt amps. So take the 90, divided by what? 0.95. We take the 90 and we divide it by 0.95. What did we get? 90 divided by 0.95 equal 95. I'm going to make it 95 volt amp. So each fixture is actually a 95 volt amp fixture. Each fixture is a 95 volt amp fixture. Okay? Then to make it so that's the apparent power for each fixture. Then if you take, how many of them do I have? I have 200 of them. Multiply the 200 guys by what? By 95, because I have 95 of them. Divide them by the voltage. What's the voltage? 120. So that will give you the amps. I for all of them. I for all of them. The second step to find I for all of them, I came up with an I 159. 58 amps. Anybody come up with 150 amps? So all of them will consume 158 amps. Okay? Right? You guys come up with something closer? All right, the last step is to take all these. I need number of a 20 amp circuits equal, you take your amps, 158 divided by what? How divided by what now? They're 20 amps. I will split them in 20 amp increments. Divide by 20 amp. And in this case, you end up with, what do you come up with? 7. Did you get a fraction?
No. 7 and some change.
Okay, so you get 8 circuits. 8 circuits. You get 8 circuits. So you can put all these on 8 circuits based on the circuit. Now, Ashley, if that was continuous load, we do the same calculation, exactly the same. Except when we come down here, and instead of dividing by 20 amps, if it's continuous load, guys, you can't load a circuit breaker 20 amp more than 80% of its capacity. So because you can't load them more than 30%, 80%, when you come over here to the 20, you multiply this 20 by 0.8. You cut it by 0.8. So you're dividing by 16. So if you do that, divide by 16, see what you get. 158 divided by 16 equal, you need 10 circuits. Had this been a continuous load, you need 10 circuits. 10 circuits to feed these babies. So 10 divided by, say, 200, I'll give you 20 fixtures on one light. Right now, if you just, how many fixtures? If you take 20 divided by 8, 200 divided by 8 will give you some change. You get 25 fixtures right now. You get 25 fixtures on a 20 amp circuit. Loading yet, but 25 fixtures. Right now, you get 25 fixtures of this type. This is, by the way, the one right above your head. That's exactly like the one above your head. 25 of them in a 20 amp circuit. I told you in residential we did what? 10, no more than 10. So, yes, sir.
When you said this continuous distributor,
Non-continuous.
no, you said
If it's continuous,
yeah,
because of heating, you don't want to overload your circuit breaker to the max. So if your circuit breaker can handle 20 amps, if it's continuous, you want it to carry no more than 80% of the 20, which is 16. Why? Because if it's continuous 3 hours or more at full load, it heats up, and the circuit breakers are not rated, manufactured, all of them except later on in bigger circuit breakers, they're not rated to work at 100%. They're not. Safety factor. Any questions about this? Any question about this?
When the conductor heats up its resistance.
Well, you size the conductor accordingly. Now if I want to go into the sizing, now you guys, you know that this conductor be what? Number what? Number 12, unless you have a voltage drop problem. This conductor will be number 12. I can put 25 fixture in one circuit, 20 amp circuit, I'm good to go. Okay. The last two are very easy, guys. So that's what I'm going to do. I'm going to give you a break in a second here. Can I move on? No? Yes? They're very easy, the last two. So this is 9. Question number 9. Question number 9, you're going to laugh at your friend Chad. But I have a couple of resistors in parallel. I'm asking you to find the equivalent. 3 resistors in parallel. Find R total. And knowing the following, knowing this baby is 10, and this baby is 30, and this baby is 40 ohm, and again ohm and ohm, 10 ohms, 30 ohms, and 40 ohms. Find the total. They're all in parallel. That's piece of cake. So this is just a bonus. So in a case like this, 1 over R total, one way of doing it, 1 over 10 plus 1 over 30 plus 1 over 40. How would you do this in a calculator? If you have a scientific calculator, guys, anybody knows how to do fractions on these? You can do fractions on this. If you don't know how to do it, just take the fractions, 1 over plus 1 over 30 plus 1 over 30. When you're done adding them, take 1 over the answer, the reciprocal, 1 over the answer. So then R total equal, I have 6.3 ohms, 6.3 ohms, and some change. How would they do this on the calculator? As I say, they take 1 over 10 plus 1 over 20 plus 1 over 30 equal. Then when you're done, take inverse. In my calculator, you take inverse, reciprocal is Inverse, where am I here? Inverse, yeah, 1 over x. Thank you. Inverse mini, which is 1 over x. When you get your own baby here, which you're not going to be using a whole lot, you can do them on this. Plug them in as values and hit parallel and get you the answer. So, okay, the last one, number 9, the last one is even easier. Yeah. By the way, just so you know, all these rules are rules of parallel circuits and inductance and all this good stuff and capacitance. They are in 1-17. If you guess 1-16, I encourage you to look at the wall 1-15. All the rules are there. DeWalt 1-15. All the rules of the parallel series and combination circuits are there. And just a reminder, you guys have all my tests are open DeWalt. All right, 10 and the last one. Question number 10. Last one, guys. I have two things. I have a capacitor, and my capacitor is the value of my capacitor is 50. Let's put it 50 microfarad. You guys remember that from the days of Mr. Ryman? Microfarad, and I have an inductor right next to it, coil, and for my coil is 400 Henry. 400 Henry. My capacitor is being burned at I'm burning my capacitor at 50 hertz. That's in Europe. And my inductor is an American baby, and I'm burning it at 60 hertz. Okay? The question is, find the impedance of these inductor and capacitor. I'm burning one of them in America and one in Europe. And I want to find the impedance, how much impedance each one of them will get. Okay? Cool? I'm going to do the Henry first because it's easy. XL for the Henry, do you guys remember that? 2 pi F times L. And this is 2, what's pi again? 3.14 times F. This is a European baby. So 50 times, no, that's the American guy. So this is times 400 times 60. And if you did this, you're going to end up with 151 kilo. 151 kilo ohm. Did I do it right? 151? 151? My 5 looks like nothing like a 5, but 151. 2 times 3.14 times 400 times 60 get you 151. Any question guys about this? Finding the impedance. 151. This is for my Henry. I'm going to call this as number 1 here. This is for number 1, the Henry. Number 2, the capacitor. I'm going to take it to the next page. When you guys are done with that one, should I take my European capacitor to the next page? Yes? No? Cool. Okay. So then I'm going to take my 2 here. Then XL. Do you guys remember what XL? 1 over 2 pi times XC. We did XL, didn't we? Yeah. XC times C times Miss F. Frequency. How am I going to do the frequency? Okay. So 1 over 2 times 3.14 times, what was the Henry? The the third. 50 micro is 10 to the power minus 6. Now that's times, where are we here, Chad? Times 50. The frequency is 50. Okay, so 2 times pi times 50 to the, this quantity here is the capacitance. And then you find the capacitive reactance. Capacitance 2 pi CF. And you get 2 times 3.14 times 50 for the frequency, and then 50 for the times 10 to the power minus 6. Okay? Do you guys know how to solve this one? The easiest way, when you have, everybody knows where the 10 to the power minus 6 came to be? That's a micro. Micro is 10 to the power minus 6. Just a little bit of info. The easiest way to solve this is to take the 10 to minus 6. You guys remember from the days of math, you shift it up to the top, it becomes 10. This becomes 10 to the power 6. And then it becomes 2 times 3.14 times 50 times 50. Now I'm talking. And 10 to the power 6 is a million, right? It's 1, and how many zeros in the front of it? 6 zeros. So it's a million. So a million divided by this number. Everybody knows why this becomes 10 to the power 6, because when 10 to the power minus 6, when you go from bottom to top, when you divide, you always change the sign of the power without getting into the math. And if you guys did this one, you end up with 60, and I approximated here, 64 ohms is the capacitive reactance of this capacitor that burning in Europe. Any question, guys? That's all. Any questions? Actually, is this hard? More or less. Here's what I expect you guys to do. All these formulas. By the way, the capacitor formulas are also in DeWalt. If you look at the capacitor formulas, all these are directly in. We're looking at 1-19. You can get all these in DeWalt 1-19. The rules for the capacitor and the inductor. I encourage you guys to utilize that baby. Highlight these pages as we go through, because they really come very handy. At one time, Phil, my friend, this is going to be your reference for all the formulas. That thing. Yes, sir. Yeah, they will two. Yeah, it's 2 parts. One part is for the inductance, and one part is for the capacitance. Inductive reactance, capacitive reactance. Yep, absolutely. 2 parts. Any question, guys? Okay, break. I want to record that one here. So the test is going to be 30 points. 30 points. 20 of them are multiple choice. And the other 10 are fill in the blank or essay divided equally or match. So 20 multiple choice, 10 match, essay, and fill in the blank. Okay. So when I tell you guys certain things, please read it. Make sure you understand the labeling, listing, and labeling of equipment. What does it mean? And who does the listing and labeling? Chad Curdy, do I list and label equipment? I'll give you a hint. UL is one of them. So listing and labeling of equipment, what does it mean? That's in the code also, listing and labeling. And who does the listing and labeling? The electrical inspector list and label? So make sure you understand this fully. Okay, cool, good that, listing and labeling, and who does that? The other thing is pay attention to when we do the load calculation for residential, there is areas included in the load calculation, like volt amp per square foot, 3 volt amp per square foot calculation. There's certain areas involved, others are not. Example, garage is not part of the calculation. You don't take the square foot of the garage when you calculate. So make sure you understand the ones that count, the square foot that count, and the square foot that does not count. Cool. Square foot that count for the 3-volt amp times square foot calculation, and the ones that does not count. When we do a volt, okay, cool. When we do a volt amp calculation, 3-volt amp calculation for residential, when we do that, does that include the small appliances circuits and the laundry or not? Does that also include the track light? If we have a track light in the living room, is that included, especially track light, is that included in the volt amp calculation or not? That's directly from the 3-volt ampere square foot calculation. Does the track light, is the track light included? Is the laundry circuit included? Is the small appliances circuit included or not? Cool? Make sure you understand that. So write them, review them if you don't know them. Another thing is make sure you know all the requirements for locating receptacles in a dwelling. For example, the rule 6/12. Every 6 feet from every opening, 12 feet in between. The rule that a wall of 2 feet, 2 feet or more wall, you need a receptacle. So make sure you understand these, the rules of laying out receptacle. They're in Article 210, and it talks a lot about laying out receptacles. In the kitchen, the rule in the countertop Zach is what? 2 by 4, always 2 by 4. 2 from every opening in the countertop, 4 in between feet. All these rules, guys, make sure you review them, understand them, where to find them. So there's a few questions about the rules of laying out receptacles. Are these rules mandatory or recommendation by code? When I say 2 by 4, is it up to you to put 2 by 4, or is you have to put 2 by 4, especially in the state of Minnesota since we adopt the code? You have to, it's mandatory, right? The rules are mandatory. Okay, so there's a few about that. GFCI location and AFCI location. Make sure you understand where do I need GFCI. That's easy. We reviewed it a couple of times. AFCI and GFCI location. So if I told you receptacle in the laundry room within 6 feet of a sink, need a GFCI receptacle. All countertop, GFCI. Arc fault circuit interrupters in an area that doesn't need a GFCI for the most part. AFCI, GFCI locations. Please review that. Everybody knows that the smallest conductor that we can use for power and lighting is what? 18? That was 18 or 14? The smallest conductor. That rule has been there 100 years ago. Do you guys remember identifying grounded conductor, white and gray? Remember when I talked about identifying grounded conductor with white and gray? And I said if the conductor is larger than certain size, you can identify it, re-identify it in the field. If it's smaller than a certain size, it has to be color coded. Anybody remember that size? 4 or larger, less than 6. 6 or less, 4 or larger. So if it's 4 or larger, you can re-identify the cables. You have a black cable, but a tape on it, it becomes a neutral conductor. If it's less, number 6 or less, then you have to, it has to be color coded, meaning the complete color coded. There's a few questions about color code of grounded conductor, guys, the white and the gray. So please understand the grounded conductor color coding. The use of NM cable. Where can I use NM cable? It's in the code. I know, can I use NM cable in hazardous location? You hope not. So the use of NM cable, the Romex. Where can I use a Romex NM cable? And where can't I use? You don't have to memorize this. In the article that talks about NM cable, guys, go in the code, it lists all the locations. Fixture web. Everybody knows what a fixture web is, that little wire that attached to the fixture. If you're using an NM cable as a fixture web, NM cable as a fixture web, do you need to support it? support it if it's a fixture web? Do you need to support it, and how far you can allow it? Is it 6 feet or 4 feet if you use it as a fixture web? So review that one. That's an article that talks about NM cable, fixture web use. AC cable, that might confuse a little bit. When you talk about AC cable, you guys can get them in 2 conductors, 3 conductors, 4 conductors, multiple conductors. So just remember that. They make them in a lot of conductors in the same cable. Talk about identifying of a neutral. What's the largest size conductor? That's probably the electrician work. That's why it could be confusing. That if you install in a conduit, it has to be stranded. That was in your German exam. The largest conductor, size-wise, that if you install in a conduit, if you install it in the air, or if you put it in a cable tray, there is no limitation. But if you put a conductor in a conduit, after the largest conductor, after which it has to be stranded or non-stranded. Is it 10 or 8, basically? Review that one. Do you guys know what an isolated ground receptacle is? Isolated ground receptacle, when we talk about the devices, I have to stay here next to that. Isolated ground receptacle, the grounding slot is completely isolated. The yoke itself is completely isolated from the grounding slot. We'll talk about it when we go commercial. So make sure you understand what a isolated ground receptacle. The spot that you ground the equipment with is completely isolated from the frame of the yoke of the receptacle. Make sure you understand that.
Ground conductor is insulated too.
Yes, yeah. Otherwise, it defeats the purpose. You're absolutely right. What is inductive heat when it comes to circuits, and what do we do to minimize it? Inductive heat. We talked about inductive heat. When you pull branch circuits and feeders, a major part is inductive heat. What is it, and what do we do to minimize it? There's a couple of questions, guys, about the code. What does this code article means? I expect you to go to the code, read it, and understand it. So anything that has a code reference in it, it's open code book. The book is open ugly, not ugly, DeWalt, and open code book. All it is. There are 2 types of NM cable, guys. Make sure you concentrate on them. Just give you a hint. One of them can be used in dry location and damp location. Others can be used in wet location. So 2 types, like if you're doing farming and all this stuff, it's a big deal. What are the 2 types? That one can be used only in dry location, the other one can be used in wet location. NM cable, raw mix. Supporting raw mix, guys, NM cable, how far do you support it from every box and in between supports? Intervals of supports as well as from the box. Very easy. NM cable, because we're doing residential. Re-identifying the white to be a hot conductor. Remember we said when you come to the switch, if you're using cables and you need to re-identify, because you're using cable to a switch, in this day and age, it's going to be kissing you goodbye anyway because of neutral. But if you are to re-identify, the code allows you to re-identify the white to be used as a hot conductor. When you re-identify, do you use it as a hot bringing power to the switch, or a switch going back to the light? Make sure you understand that one. When you re-identify it, do you use it as a hot conductor bringing power to power the switch, or the switched hot that's going to the switch, or switch loop? For switches, guys, and I don't expect you to memorize all these, but probably you would know that one. For switches, when you say S4, what does it mean and how many terminals in it? S and next to it 4. Anybody can tell me what an S4 is? Yeah. How about if you see an SD next to it? S and a D. Dimmer, yeah. So make sure you pay attention to these. S by itself, single pole. And how about S next to 3 next to it? Three-way switch. Okay. And how many terminals with each one of them though? How many terminals? 4-way, 4 terminals, 3 terminals, 2 terminals. A terminal is the 2 sides of the switch, or the 3 or the 4 sides. Gentlemen, that's all we're going to be. The test is very easy. There's a lot of material that we covered, guys, but that's the most important thing I want you to concentrate on. Any question? So come Monday morning, we'll do the test early Monday morning. Yes, sir. Okay, here's how it's a 30. All my tests are the same, all of them, except the final. From now until you graduate, they're all 30 problems. 20 of them are multiple choice, and 10 are divided equally between fill in the blank, essay questions, and match. So they'll give you like 3 of each. Make sense?
And the calculation is only.
Oh, and the calculation. The question is the calculation. My calculation is 10 problems, exactly like you guys saw. 10 problems. I can be a gimmick. I'm not a gimmick guy, but I don't like to trick people. But here's what I can do: change certain things. If it's single phase, I might throw a 3-phase at you, like I told you, and that's about it. These are the most important thing I want you to get. We went over them, get them, and we move on. Any question, guys? Okay, that's it.